Hi, I'm going to run you through this notebook of the GLM. I'm going to do so step by step and try to explain things that may not be clear from the text inside the notebook, but I'm not going to read the entire text of the notebook out loud. So I'm going to run from code cell to code cell and try to implement the solution offhand. Yeah, let's see. Now this is being run from my teaching account, which means that this should function similarly to how it functions with you. Like in your Google Drive, you are likely to have loaded the data in exactly the same location and this and that. It's not the Google account that was used to create these things. So let's see how this goes. It seems to have mounted a Google Drive. And I allow this notebook to connect to this account's Google Drive. And that's allowed. Great, so that seems to work. Now, of course, we need to import some modules. And let's see, where are we? So the first time we do anything, we have to calculate the mean over all samples of the predictor. For the predictor at index j is 4. This is the fourth predictor. Yeah, so most of this is already pretty so usually the answer is given in the assert almost equal thing below, right? So this here, there's an array called R, and we're going to take the mean over the fourth item here, right? And of course, then once you've done this, that means that the test is passed, right? So this assert almost equal asserts that the values of these two should be equal. If they are, it passes. That is, it will return true. And if it doesn't, then it will return false, as you have noticed if you've created a wrong answer, such as this one, right? It is not the same, whereas here, now it is. Yep. Great stuff. Now, in the notebook, we're going to use this least squares approximation function, and that is implemented in the linalg subpackage of NumPy. So we're going to use that. And there are specific other ones, but in principle, the math underpinning these things is all the same. So first, we'll create some random numbers. We'll create an X, an independent variable, and a dependent variable, i.e. data, that's called Y. Yeah. So here we're creating a multivariate normal data with a pre-specified covariance matrix. And because we have two variances, or two variables, this multivariate normal, we have a 2x2 matrix specifying the covariances. And here the variances are on the diagonal with a value of 1, and the covariances are 0.8. So this 0.8 we'll see the result of later on. Now, once we've created those data, we index those and specify that there should be a new axis at the bottom. So then we can test what the shape is, and it's 30 by 30. Yeah? So now we have 30 variables, like 30 numbers in X and 30 numbers in Y. And we have created them such that there is an interrelation between them, namely those covariances. So what we need in a design matrix is this constant predictor, which we create here, which is just a set of ones. That should always be a set of ones. And then we stack them together and now have a two-dimensional X, which contains that random number that covaries with y, and this ones, right? And you can see from the shape, it's now 30 by 2. And we can also just print it out, the numbers, and you will see then that there's a ones, and then there's this random number thing going on. Yeah. This is all nice and good, but that is not what you want to be looking at. We want to look at what these numbers have in common with y. So every number here has a sort of I don't know, twin in y, and we're going to scatter those. So this is what we get. So we get a cloud of points that's scattered such as this. I won't go through the entire theory here, of course, because that's what you're supposed to read. But we're going to just do some math here. I'm just going to show you what you should be doing here. Yeah. So we're going to create a y hat from a set of beta weights and an x. Yeah. Now, there's a shape of 100 by 2 for this x, and this one is just 2 rows. So usually what you do is you could do this literal sum where you multiply, you go over j's and you multiply with x's and betas, so because values from these x's and these betas, but we won't. We'll just do numpy dot, which is implementing exactly what that is. And I always forget, but I'll just try and see if this works, whether the dimensions are aligned. If the dimensions aren't aligned, for example, if I do the transpose of this x, it will give you an error such as this. So this now makes that work. And we can check with this assert almost equal that this is our solution. Now you see here, I've taken a different route to creating the same numbers. I use the numpy dot dot function where this x and these betas are arguments, but you could also say this x dot dot these betas, and that's the same thing, same result. It's just that here you use a sort of more literal programming or procedural programming thing, and here you're using an object-oriented programming approach. Now let's see. We can also try to find betas by doing least squares. And that's what we're doing here. We're modeling y using x, and we get some output. Now this output is a tuple, so we need to index it. The first values of the output of least squares is the betas. So we can check for the betas. They are 4 and 0.8. So there's a lot of thought into this, right? Why do you only have 2? Or why do you have 2? And now we can have a look how these betas explain the data, right? We have to combine it with the betas. We have to combine with the original x's. That gives us the possibility of constructing our explained signal, this y hat. Now, the same way of doing it would be to do this by means of a dot product. And you see that they are exactly the same values, right? So this is just performing that weighted summation that the dot product also does. So that's our y hat. Yeah, it's just faster. It's less code to write, and usually also faster to implement. Like, so the computer actually performs this faster too. So let's see what that does. Yeah, so here you see why we're calling this linear regression. The line that we fit is a linear line. It's a straight line, which means that this is linear. You see that the predicted y captures the main sort of direction of the data, but it doesn't capture all of this noise. It's also placed high enough by the intercept such that it actually lands in the middle, that it's not stuck at 0, 0. That's what the intercept does. It allows us to vary up. Let's see. Oh yeah, then there's this. So you can actually, from your fits, you can actually also predict data that lie outside the original range of the data, right? So we can extrapolate further. So let's have a look at the structure of the residuals. All right, so this is the residuals. So these are the distances of the points of the data to that best fitting prediction, that best fitting model. We can calculate the mean squared error. Right now, what's the mean squared error? Well, it's just the error. So that's the residual. I think we have a y and we have a y hat, right? So that's our residual. It's the difference between the data and our best fitting model, remember. That we need to square because it's the mean squared error, right? And then we have to take the mean, which we can do thusly, right? So that's our MSE. Now we're going to assert almost equal on exactly what I just typed, so no problem, that's true. Okay. So another metric is R squared, that is the proportion of explained variance. Yeah, this is how you calculate that. So explained variance is just those squared residuals summed. You can do that for the data. So this is the variance of the data, and this is then the variance of the residuals. And with this single subtraction from 1, you get the proportion of explained variance instead of the proportion of unexplained variance. So we get an R squared value of 0.5, almost 5. Yeah. Okay, here we go. Now we have an actual data set that we're going to try to explain. And now we have to go through all of the previous steps, the ones that we saw before, right? The running of the regression and all that, and then see what we come up with. Yeah. So let's see exactly. We want to, get R squared. Okay, so we calculate R squared after we run the regression. We have an X test and a Y test. That's great. Now this is quite an exercise immediately, right? Because it requires you to start putting together all of these earlier steps. So the first step is to run the linear regression, right? So that is imported like so. I have to check. I always have to check. Where are we? Oh, I can just run LSQ, least squares like this. So you know what? I'm just going to copy this code and not care. And you are very much free to do the same. So in this case, we're going to use X test and Y test, of course. And this R cond is none is just there so that the calculations take place in a specific way. And you can do all of this in one go. You can also say, and these underscores are just placeholders. So this means that you just get the betas in one go. You don't have to index the tuple that came out. You're just throwing away the final parts. Now, having the betas is nice, of course, but as you remember, we need to construct y hat. Right? And we did that by dotting, not datting, Thomas, dotting the design matrix with the outcoming betas. Yeah, so that gives us the predicted time course. And so this does all of that summation and what have you. So then we can say, of course, the difference between the data y test and our best fitting value is this. So I'll call that residuals, just so we have a word for it. Now I can go through this, right? I can go through this R squared value. Yeah. And let's see, we have residuals, that's y minus y hat, right? Boom. Take out some brackets, and we have a y test. See, it's okay to copy stuff. That's not a problem as long as you know what you're doing. So we're keeping these numerator and denominators in there. And let's see if this does anything, whether we get an R squared value. There might just be also, I was also expecting an error. Happens, you just try, see where the error comes from, that sort of thing. But it seems to work now. So this is all you need. And let's go through these different steps one by one. So this is what we started out with. And so first we get these weighting factors, right? Weighting factors for each of the regressors. Those are beta weights. Then explained signal, right? Our best fitting, this is our best fitting prediction or model, time course, or yeah, model. Then our error, right? So that's the epsilon in all of those equations. And it's called residuals. And then explained variance, right? Calculate the proportion of explained variance. How much of the total variance of the signal did we explain? How much is left in the residuals? Now, Smarty Pants might conclude that you can also look at the variance of the model and then divide by that and then subtract and that sort of thing. Right? But we do it like this. It's better, trust me. Ah, yes. Now we have to go through the explanation of why there is an intercept in the first place. Now, that's an important question. So here's an example of what happens when you don't have an intercept, right? You can still perform least squares. Now, because our x no intercept is only a single vector, what you can do is, well, you can just do least squares. There is now no intercept in this x, so you get out a single beta weight. And that beta weight, you are going to now just multiply with x no icept, right? So multiply instead of dot with the design matrix, which is now a single vector. Now that result we can plot immediately, right? Because we now just have a y hat and so forth and so forth. You see that it's still a linear regression in that it ends up with being a line. But you also see that something salient has happened. When the last time we did this, we fit this something value larger than 4, right? And that was one of our beta weights. And where did we get it? Well, the beta weights of my model are 4.2589 and so forth and so forth. So that's what you see here. That intercept was there. And now we don't have that intercept. And you see the result. Not having the intercept in your fit means that now your best fitting line has to go through the origin, right? It's being forced to go through the origin. And what that means is that the role of including the intercept in the design matrix is that you allow the model's explanation to veer away from the origin and thereby better explain the data. What do we have to do now? Ooh, let's go. File not found error. To do. Well, that's not supposed to happen. Wait a minute. To do.mpz. Would it be then in data.mpz? I apologize for that error, but you see, you can find things. Let's go back to the table of contents. So let's check the shape of x and y, right? So how do you do that? Well, this is a notebook, so I can just say this, because it will print them automatically. Will show me the output of this cell. But if you're neat about it, of course, you would do this, which ends up more or less the same thing. Right? Now we need to add the intercept. Yeah. Well, okay. So we go xint, right? that's our x with intercept, and that will be np.h stack of np.ones of x.shape size of the 0th of x.shape 1. And I do think that, yes, np.ones wants a tuple in there. So this is how we have to do so, right? So this defines the intercept. It makes a matrix of, in this case, 1000 by 1. And what we do now is add x. Let's see if this works at all. I think also HStack likes tuples as inputs. So let's see if this does anything. Hey, now just to check, right? I don't know what I'm doing. So I'm going to check what the shape of this x int thing is. And indeed, it is exactly what we wanted it to be. Yeah? So now we get betas, right? So that is betas is LSTSQ of x with an intercept and y, and we are going to take the 0 thing, and let's not forget to do this. Cond is, was it true? I have no idea anymore. None, that was it. So this cond thing changes how exactly this is implemented in the math underpinning things. What am I doing here? Or rather, what am I doing wrong? Rcond, of course. You see, you have to just find a way to look up the right code. Mean squared error. Let's see. First, what is the squared error? Well, that is x int dotted with the betas. Remember, that is y hat, right? And well, let's first call that y hat. Y hat underscore to do. I'm typing too much. I hate that. So we have our x int dotted with the betas. That's our y hat. Now we want to take the difference between y hat to do and y, and it doesn't matter which order we do this in, right? We could also do y minus y hat because we're squaring this after that, and that will make all negative numbers positive. So this is the mean squared error, yeah? And now we have to calculate the r squared, yeah? And we have to put in this r2 to do. Who came up with these words? You know, and I'm lazy, so what I'm going to do is just take this back again. And I'm using residuals here, so you know what? I'm just going to define a residuals variable here. That's just going to be this. And I'll add it there, right? So now I have this residual. I have my y, right? So that would be y. I guess, yeah, that was the name of the data here. So this means that R2 to do is done. I hope, because now I'm going to check. Yeah, so there are no hidden tests, of course, here. But there's no assertion error, right? If assert goes wrong, there's an assertion error. Let's check, right? If I just make up an answer, you'll get this assertion error, right? So apparently we didn't go wrong. And I'm glad that that's not the case, because this is the sort of thing you do every day when you work with fMRI data like I do. Okay, that's step one. I hope it's clear why we have to incorporate the intercept, and it's also, and I hope that it's also clear that it's not terribly, it's not that much work to go through the cycle of performing the GLM yourself, right? So it may have sounded like magic before, but it's just a very strict predefined set of steps that you have to take that you create the inputs to the next stage with the present stage. Right? So you're really building an analysis step by creating all of these different components. So let's go on with the next, where we're actually going to look at fMRI data. Yeah, so here, the data are created by an fMRI experiment or a simulated fMRI experiment, who knows? And here we have an example voxel signal, right? So you see that there are certain activations that seem to be occurring once in a while, and there seems to be this sort of stable thing going on, right? So there seems to be a baseline from which there seem to be these excursions of data. Now you can think for yourself. And so this is just to highlight the difference in visualization, right? If you plot these as points, this is what it looks like, and you don't really see the connection between the points, right? But if you literally plot that connection between the points, you start to see that you start to get an intuition far more for the fact that this is a time varying signal, right? So this is important to keep in the back of your mind. So here we have the outline of the experiment. I'm not going to bother with that. I think you should read it. And there are two types of events in this experiment. One is onsets of squares and the other is onsets of circles. And we can concatenate those if we wish. Right? So this is the squares and this is the circles in the end. And that gives us all of our events. Now what we can do is use these as indices into an empty array and set those to 1. So what that means is we have this empty predictor array that's 1 whenever an event happened. Yeah? So this actually tallies every TR in the experiment. And we are going to subsample. It's been a while since I looked at this. So apparently we have 400 time points in our data. Yeah, that sort of makes sense. However, yeah, well, I'm not going to go into what may be wrong here. Let's just continue. Oh yeah, so because all of these are even numbers, you can do this even number subselection and you get all of the events, I do think, don't you? 8. Apparently you don't. Oh, we're only looking at 1. Yeah, so I'll go into that later. So here we see events happening in our experiment in the orange line, which is our predictor. And then we have our voxel time series on top of it. So let's start to see how we would go about this, right? So again, we want to set up an analysis, a GLM analysis, and we're conducting a very simple experiment now. So actually what we end up doing is exactly the thing that we did in the previous exercise. And so because I am so lazy, I'm just going to take all this code and start working with it. Can I select more text? I can. Well, so I'm going to try and dump this in that single. Here we are. Boom. What did we call the data? Voxel signal. So no longer we have any Y's. And this is now, what was it called? Predictor? Predictor all DS? Yeah, predictor all downsampled. Fair enough. yes. So we'll just make all of these again. This is not the neatest way of doing things because I'm renaming variables all the time. And you can imagine that if you have a longer notebook, it becomes a bit difficult to understand what was what exactly, because it kind of depends on what cell was being run last. And that can be problematic. So in everyday life, you don't want to be as sloppy as I am now. It's probably going to crash, of course. It's miraculous that it didn't. And so this means that I can also just take out all of these cells because they have lost their purpose. Let's see what happened really, right? So we just went through this enormous, oh, now I do have all of the points here. So we have our true signal and our predicted signal, and you see that we are getting some beta, right? For both the intercept and for our predictor, right? So again, what I've done here is I've created an intercept, and there was this predictor, and I'm regressing those with least squares, then dotting them to get a y hat, right? So that is taking the intercept and the beta weight for the predictor, and then multiplying and summing them. This means our intercept value, so that's the first beta weight coming from the least squares, is something like 0.3. And then there's another one also around 0.3, because that's the multiplication of that single thing. So here we have our best fitting explanation of the time course, but we're not really explaining much of the time course, are we? Let's have a look at this. Right, so we have, so here we have our beta intercept, right? Here we have our beta stimulus, and there's just a lot of signal that we're not explaining here, yeah, and that is problematic. So let's start by having a look at how we do this, because if you take a step back and you look at like, here an event happened, and then there's this whole bulky signal that's happening afterwards that we're not even trying to capture now, and that's problematic, right? We need to be able to fit this bulky response there, right? And we know what that bulky response more or less looks like. It's this HRF shape, yeah, and this is what that looks like. It's the hemodynamic response function shape, and we just use this very specific set of functions for that. Any fMRI analysis package will implement these. Now, let's look into detail, right? If we take these stimulus events happening at these points in time, we convolve them with an HRF, what we get is this convolved predictor time course. Okay? So convolved stimulus vector. Where did we do the... Oh, here we are, np.convolve, right? So NumPy implements this convolution by just this function. You take your random stimulus vector, your difference of Gaussian HRF, it performs this convolution, and this is what you get out, right? And that's what this does. Now, because this is has a length of 24 time points, this HRF, what you need to do is take out, if you do this full thing, convolve full, it actually, the resulting length will be the original length plus 24. And of course, then you have to take those final ones out, and that's what you're doing here, right? You're only taking those values from the convolved predictor where you already had a value in the original predictor. So let's see what that looks like before and after convolution, right? So even though the events happened at some time point, we expect the maximal response 4 seconds, about 4 seconds later, right? And we also expect a much longer response. Now let's see what happens when we use multiple stimuli in a row. And this is what you read in that paper by the Boynton and Heeger. If you have a stimulus that's 3 times as strong, it will give you, and this is very close together. So what this means is that there's a stimulus that's 3 times the duration, and it's the same as having a stimulus that's 3 times as strong. You get a summation of the Bolge response, a linear summation of the Bolge response. And this means that we can use this entire GLM framework to analyze our data. You see that if you have a block design type experiment, what you end up with is also a very blocky time course in your predicted data, right? So this is, again, a predictor. And let's see, where are we? Oh yeah, so in many experiments, you have events happening at random time points during the experiment. There are reasons why you would want random time points in an experiment, not just because subjects would not be able to expect the onset of a stimulus. And what you end up with is this very smoothly varying version of that same, of that time course, right? So it's very hard to distinguish these events happening here. But knowing when these events happen gives us a way of constructing a model time course that we can then regress onto the data. Yeah. So now we still need to downsample, and we do that in the same way as we do here, right? So you don't really see the difference here, but this is something that you do a lot. That is, because these events don't happen on the TR necessarily, but they're jittered relative to the TR, what you do is you can construct, or you have to construct your convolved design matrix at a much higher temporal scale, and now we have a factor of 2. And then resample it down to whenever the measurements happened. Now we have a setup where we have a predictor that's going to give us, this is our expectation of what signals should look like in the data. And now we can use this to perform a GLM analysis. So let's see what this ends up doing. Now here you see the amazing result here is that fitting using this hemodynamic response function gives you a much better explanation of the data than you did have before. Yeah. So here's that example of what it looked like before, and here's what it looks like now. It's much better, right? We're explaining much more of the variance of the signal. You can immediately see that. So let's look at the beta weights. Yeah, so that beta weight just increased by a lot. Yeah. So again, we're going to zoom in and inspect what we just did, right? So now we have a beta weight for a stimulus, for our stimulus, and we have this beta weight for an intercept. And we are much better at explaining that time course shape that we see here. Yeah. And like I already said, we also see this increase in the statistics that we calculate, the mean squared error and the R squared. So that goes, that final R squared goes from less than 1% to almost 25%, which is pretty okay. Yeah. So what we've done up until now is we have set up only a single onset type in our analysis, right? We've created a set of only a single regressor, and we haven't cared about whether there were squares or circles being shown. So now we're going to do things differently. We are going to now separate these two types of events into different predictors and fit them separately. So each of them will get their own beta weight. And because, of course, yours truly is lazy, we're just going to copy bunches of code. Yeah, I'm just going to do this. Boom. Of course. So the intercept is going to be the same for both of them, right? So when I stack them, that's going to be fine. This is already downsampled. Great. Let's first convolve. I thought this was, yes. Right, so we convolve and immediately use the indexing at the end to use the same href. And this we wouldn't need to do because they're all the same. But oh well, here we are. We only need one intercept. So that means that we can I'm not going to downsample here because we're doing a very simple analysis. So I can do this, just take every second data point. X square. And we could also do this with circ. So now we have two design matrices for predicted square and predicted circles. So I have no idea what I'm doing usually. So let's first try to plot these before we do anything else. Yeah. Oh wait, I'm doing something wrong. I'm making two separate design matrices, which is not what we want. We want to put them in the same design matrix. So we want to put that here, and that is just called X mu. It's late. Forgive me. No, it's not the problem. This was the problem, an extra thingy. Let's see. Object2D for desired array. Let's see how we did that before, because of course we already have code that implements this, and it's often just a bit silly to reinvent the wheel all the time. So what I just did without you seeing it was to delete that extra dimension that this created. So now I just have a simple 800 vector, and that goes into np.convolve very easily because now it conforms to the shape of the href. Now, the intercept we're creating by just integer dividing the size of the predicted to circ conv thing. And then I still have to subselect those even time points. That's all fair. It's not the prettiest way of doing it. Normally you would subselect, you could subselect like so, right? So you're already selecting the odd time points up until that point. Then you could do this, you don't have to have the number anymore, and this would also work. So what's happening here is we're creating these separate regressors and then stacking them all together with that intercept, right? So, but we're not interested in the intercept, but let's just have a look at what these predictions look like over time, right? Because that's interesting to first have a look at. And here you see that original regressor that we had that yoked the responses of the two different types of events are now separate time courses, which means that we can get separate fits of the two types of events bold responses. Yeah, so we'll get there by taking this x new and fitting it using least squares. And I'm sort of assuming that we're going to fit voxel signal still. We're going to get these betas, right? So what that means is that immediately we can also take x underscore new dot with the betas to get that y hat. Here we are. So that's our y hat. Apparently, I'm supposed to call that new. And oh, b new. Okay. I don't know. And again, of course, MSE new is that squared error. So that's y hat new minus voxel signal squared and meaned, right? So that is np.mean of that thing. Yeah. Similarly, we can do the r squared, right? And again, I'm so lazy that I'm going to just copy the code from the r squared. Here, and this is all doing that same thing in one single go. Yeah, here we are. So, of course, that's called R2 new. It's a much better name than R2 to do, which is a tongue breaker. So here we are. Am I making a mistake? Is there a, oh, yes, I should have put a 2 in there. Let's check. I may have done this in the wrong direction. We might get another error, incompatible dimension. So yeah, I'm fiddling around a bit with these because I had changed these dimensions. It doesn't really add up anymore. So now I should do this. Now trying to fix the problem I just created by adding a dimension using indexing, but I'm now doing so after all the convolutions. And so I fixed the problem that I created when we started with this, right? And this operation just fixed the problem by putting an extra dimension back and then being able to perform HStack. That now means that all of these dimensions line up and we are good. Yeah, this is all nice, but we've now just calculated things and we haven't actually looked at whether this improves anything, right? So let's first look at print of betas. And we don't have to redo all of the calculations. That would just be silly. So we'll just, you know, add a code cell. Now here we're printing the betas. We get some intercepts. And, let's see. I think I may have done something wrong because I was expecting only 3. Maybe I should have used the word be new then. There we go. We have 3 now. And what you see is that our intercept is more or less in the same ballpark as we had before, but now the 2 beta weights for the different regressors actually have quite different values. One is almost twice the other, right? And of course, when we then plot our y hat new and our voxel signal, that becomes apparent. You see, oh, should have plotted it the other way around. Here we are. Isn't that gorgeous? You see that some of these events are just much taller in their response than others. Yeah. Great. So this extends to many more types of events and extends in parallel across all of the voxels in the brain. Okay, we're now going to look at different shapes of the HRF. I spoke a bit about that in the lecture. So this is what we ended up with just now, right? Did it just, oh yeah, this actually implemented everything that you were supposed to see happen before. So you see that the orange ones are taller than the green ones, which is exactly what we found before, right? This just zooms in nicer. What you do see is that there seems to be a temporal mismatch between the response that we predicted and the actual data. So can we try to start to fix this? So what we can use is three different HRF shapes where we have an original HRF and then the temporal derivative and the dispersion derivative, and you can combine these to create HRFs of varying shapes. So here you see that when you do so, so this actually exemplifies what I just pointed out in the original data. So now we can do something where we regress with the temporal derivative. And in essence, what the temporal derivative does is it allows you to shift the HRF in time. So this can then shift. And when you add the dispersion derivative, this allows the HRF to become wider also, or narrower, whichever the sign of its effect. So this one you want to go through yourself. We want to convolve these predictors for squares and circles with the different HRFs, then get the betas and so forth and so forth. So what I'm going to do is go through this. You might hear my brain start to crackle. But all in all, we don't have to do much different from what we have already done. That is this, right? The only thing that we now need to do is take what we've done here, but do it 3 times, not just for the standard HRF, but also for its time derivative and also for its dispersion derivative. And then, let's see, where are we? Yeah, so here we are. So here we have a difference of gamma HRF, but we want to use, yes. So circle conv 3, yeah. So we'll just duplicate this 3 times, well, twice. And with that, we're going to index them differently. And the only thing that's different between these different regressors is the shape of the HRF that we used convolve with, right? So the predictor, the initial predictor is the same, the downsampling is the same, everything is the same. It's just that we're using different different HRFs. So this is the dispersion derivative, and then, okay, so we're using SG and so SGHRF. Yes, so that's not a double gamma, but a single gamma. SGHRF temp, and then we have an SGHRF, guess what, dispersion. And so these are going to be the same. Boom. Yeah, that's all of them. Of course, we do need our intercept, and now we're going to just put them all together by repeating text. It's not what I would have wanted, but here we are. I have to say, I'm used to faster editors. I'm just waiting for the code completion, and it's not happening. Very frustrating, I can tell you. Now, this already is a line of code that is too long, I can tell you. So you don't want to have this sort of thing, but oh geez, what happened? What did I just do? Oh, nothing wrong. So here we're back at the cell. I accidentally swiped with my, so yeah. So in order to gain more of an overview, what you just end up doing in many cases is you just copy your code like so, and then boom. And all I have to do now is do this. I don't know if there's, does it? Yes. So you can do all sorts of tricks if you know how an editor works. And we can do plots of xt new. Yeah. Xnew.t, because that will allow us to plot the time courses of all of the regressors in X in one go. So we don't have to call plot over and over. Voxel signal, I suppose, remains the same. Xnew. Yeah. Why not, right? Boom. Where did I go wrong? Oh, here we are. Yeah. Oh, one has 800. Oh, I'm still using this wrong. Ah, here you go. Yeah. So I should have used this one. Right. So this one still had the wrong size. And apparently I'm used to looking at things in the wrong direction. So here we have our time courses of the different regressors. You start to see, well, here you have your intercept, of course, and here you have these three different types of response that happen around the time of every event. So that's not really a very insightful way of going about it. So I'm just going to use a separate function called imshow to plot this. And now it looks horrible, but it won't in a bit because I can adjust the aspect ratio of this plot. And I'm just going to guess that it needs to be smaller than that. Yes, and make it even further, even smaller. And so what we're looking at now is an image where here we have the intercept, and for every column in this image, we have one HRF shape. So you have the standard HRF shape for the square events, I guess, circle events, and then the time derivative and the dispersion derivative, and the same for the other types of events. This I've all done, and this isn't tested anymore. Yeah. But we do have a y hat that I want to quickly go through and plot it, right? Because that's always good. And now I'm going to comment this out because that would just ruin the plot and I'd have to write a lot of code to fix it. So this is great. And you see that we're actually capturing the data again much better. And I'm just going to print the latest R² to evidence that fact, right? So we're explaining half of the variance now. Okay. Great. So statistical inference. Let's see. So we have some weight height data. And we've already gone through these quantifications of beta weights and mean squared error. The problem with this sort of thing is that you can convert everything to a different unit, which we are doing here. So instead of meters, we're going to use centimeters. So that means that we can repeat this whole thing, right? So that's this. But now with centimeters, right? So I'm just, again, you notice I'm not writing that much code. I am just looking at what I should get from the above cells. There's a 100-fold difference. Oh. So this dependence of units for many of the quantities that we are calculating here is problematic, of course, because you don't want things to be dependent on your units. I've explained to you that the fMRI signal really doesn't have units, so there's really nothing to base yourself on. We have to we won't talk too deeply about design variance. I won't go into that too much, but it is a way of quantifying the statistical properties of the design matrix. And that means that we can now calculate noise and calculate t-statistics based on betas and residual variance, right? So if you go through this, here's the sum of squared errors. We calculate degrees of freedom from the amount of time points in our data and the rank of the design matrix, that's the amount of columns in the design matrix. And we get a t-value. Now we want to repeat the whole thing for centimeters, right? So again, right, this is what you do. You calculate the whole thing. The design matrix doesn't change, of course. We just have a new y. And that was y underscore centimeter. So I'm going to go through yep. Oh, here there's another meter. It's not supposed to be there. CM, right? Let me see. Am I still good? Y hat, sigma hat, sigma hat. Yeah, maybe that should be CM, right? In order for us to remain there. Yeah, so now we have the design variance. And we want to make this centimeter. Wait. I think I'm doing something wrong because something's still T-values just exploded by a factor of 100. So I'll have a look. So here you see the problem. I was still calculating the errors based on the original y and not the y centimeter, right? That, of course, will inflate your errors almost by a factor of 100 and thereby cause all sorts of problems. And now I'm also still using sigma hat and not sigma hat centimeter there. And here we are, right? By running exactly the same analysis, but now performing calculation through t-statistics, which is based on the amount of variance that you explain versus the amount of variance that you don't explain, you are stable in terms of your statistics. They don't depend on the units of your of what went in. Right? Now we can calculate p-values based on the t-statistic. We just need to take into account the degrees of freedom and in this case multiply by 2 because we're doing a two-sided t-test, and we get that there's a hugely small p-value, right? And this happens a lot. You get t-values like this, you know that it is significant regardless of whatever amount, whatever test you do. These are such small numbers that it becomes really hard to visualize. So in many cases, people just end up looking at the t-statistic. So here we're going to have an analysis with different faces, different expressions, and we're going to analyze these data in exactly the same way that we've already done. We now have an X that we take from the data, and we have a Y, so we're set up and we can just run it immediately. We have a bunch of beta weights on our data, and right, we can extract a specific beta weight, namely this the third beta weight, which is beta male SAD, right? So that's this SAD expression beta weight thing. And we want to test with this contrast vector what the statistic is for a response, whether this voxel showed a response to SAD male faces relative to an implicit baseline. So there is no other element in the contrast vector. So if we want to test a emotion effect in male faces, what we want to do is subtract betas and test whether this difference is significant with a very similar type of t-statistic, etc. calculation. So that's what we end up doing here. Here we do it by hand. We get this difference in beta weights, but as you've learned from the dot product, what we can also do is set up a -1, 1 in this vector and calculate the betas in the calculate this difference by using this dot product type calculation. Here we are, it's the same value. Yeah. We could also do a contrast between male and female faces, and the way that you would do that is 1s here and -1s here, right? These are all the male faces and these are all the female faces. Again, you can do this, you can calculate this contrast in exactly the same way. So this is the contrast in terms of the beta weights. And there you have it. You could also, and so here you have this freedom of creating contrasts even after you've run the GLM, right? So the beta weights are in memory, the sum of squared errors is in memory, and we can just run this by, for example, whether there's a difference between sad or happy on the one side and neutral on the other, regardless of a gender. And that is the way that you would codify that. It needs to be balanced, as you see here, right? So there should be an equal amount of positive weight as there is negative weight in this vector. Yeah. So we're going to create a contrast. Oh, sorry, I gave you the answer. But it's also there. Sad faces, regardless whether it's male or female, more than neutral faces. Okay, here we go. So first of all, we take this as an example, right? And we're going to do sad faces more than neutral. And neutral was, and I have to check, of course, so I'm just going to navigate upwards. Okay, so sad and neutral. Okay. So my contrast vector is, I'm not using this. This is sad, and this is neutral. This is not part of this thing. Sad and neutral. And of course, I'm going to just copy most of the code that I need to write. There's a contrast to do. That is cvec times beta's sum. Let's see if we made a mistake. Apparently we didn't. I'm sweating whenever I do these tests. Yeah, so this is trivial. I'm not doing this. Now, in order to get a actual statistics out of these types of contrasts, what we need to do is employ the design variance. We've already created this function that allows us to specify a contrast vector that will then calculate the design variance for specifically this contrast between these predictors. And we can just calculate that that value for the design variance.